This video investigates the radial motion of a massive particle in a Schwarzschild space-time from the point of view of the proper time of the particle and the coordinate time as measured by some observer. The world line of the motion of this particle is plotted to reveal the limitation of Schwarzschild coordinates. So let's follow a massive particle on its radial approach towards a Schwarzschild mass here, M. So here's our Schwarzschild black hole, and the particle is going to start some way off and travel on a radial path. Now let's say this particle carries its own clock with it to determine the proper time elapsed as it moves along this radial geodesic. Alright, from the first video in this series we found that the proper time as a function of the radial coordinate is this object here. And so we can determine the proper time elapsed according to the clock that the particle carries with it as it falls from some coordinate value out here onto the surface of the black hole and then into the singularity. Alright, so how long does it take for the particle to reach the event horizon of the Schwarzschild radius, or the Schwarzschild radius, sorry, I should say, for this mass? And we're going to call R infinity just 10 units of gm on c squared, so that's far enough away for the space-time around the mass to become sufficiently flat. Hence we can call that R infinity. And we want to know how long it will take to reach the event horizon. And the event horizon is at 2 lots of gm on c squared. So substituting that in, our final destination is 2 gm on c squared, the event horizon for this black hole. And we put that in here, and when we calculate that out, we'll end up with this value, 467.63 lots of gm on c squared seconds. If we then wanted to know how long it would take the particle according to its own clock, the proper time of the particle, to reach the singularity at r equals 0, starting from the same point here, 10 lots of gm on c squared, then the same value here, the final value will be r equals 0, so the one part of this term above will disappear, and we'll just be left with just this part here, the starting value. And when we calculate that, we get a slightly longer period of time, but not much longer, 471.41 gm on c cubed, units. I should have said c cubed up here, units. And scaling this problem in terms of units of gm on c squared, this is what we get. So the particle reaches the singularity in a finite time, and we found that in the previous video. Now, let's look at coordinate time. So an observer not travelling with a mass records at some other point in around the space-time there, records the time taken to be given by t is this object here, and this was also found, how this result came out was found in the first video in this series. So have a look here. Just note the natural log of the absolute value of this expression in here. And we note that as we approach the Schwarzschild radius, or the event horizon for the Schwarzschild mass, at 2 gm on c squared, we note that t goes off to infinity. If you note here, if we plug in r is 2 gm on c squared here, this becomes 1. Square root of 1 is 1, minus 1 becomes 0. So this goes asymptotically, this whole expression here approaches infinity as we get closer and closer to the event horizon. And we'll see in a plot shortly what that means. And this plot will help to show how coordinate time behaves on both sides of the Schwarzschild radius, because the absolute value allows us to have a look at the region inside, allows us to plot the region also inside the event horizon, and we'll see there are some complications with that. Alright, so when we do plot that, let's say starting at 10 units of gm on c squared, we scale these axes r c squared on gm so that we just have units, numbers only, 10 gm on c squared, and the particle moves in. This is the coordinate time for the particle as observed by some observer outside, not travelling with the particle, and see that as the particle approaches, according to this observer outside the mass, as the particle approaches the event horizon, this time asymptotes becomes arbitrarily close to this value here, but never actually crosses it, and takes, according to this observer here, an infinite amount of time to reach the event horizon. Inside the event horizon, though, plotting the same coordinate, the Schwarzschild coordinates, we end up with this object in here. We'll just go, notice the axes are scaled as well. Okay, so let's just have a little bit look at the local light cones along this trajectory. Now here, if we have a look at the same plot again, and we look at the local light cones here, this region is roughly close to flat space. It's far enough away from the mass. The local light cones have the 45-degree angle that we're used to, a flat Minkowski space. And as we move in, we notice the light cones closing up, the local light cones closing up. And as we get asymptotically close to the coordinate singularity. This is a coordinate singularity, not a physical one. On the other side, what we notice is that this coordinate comes down here, appearing to show the light cone tips over and points towards the singularity, r equals 0. All along here is r equals 0, and the local light cone tips over as the particle can only move towards the singularity. Once it's crossed the event horizon, it can only move towards the singularity, so the light cone points in the right direction. The only problem is, what it's showing here is as time decreases, as r approaches 0. So as we go approaching from the coordinate singularity at 2gm on c squared, the event horizon, the Schwarzschild radius, as the particle moves inwards away from that, time appears to decrease. And that just shows the limitation of the Schwarzschild coordinates across this event horizon, across this coordinate singularity, across the Schwarzschild radius. And so what we need are a better set of coordinates to probe what is happening below this apparent singularity. And it's only a coordinate singularity, it's a result of our choice of coordinates, the Schwarzschild coordinates, and there are better coordinates we can look at. And in the next video, that'll be the goal, to look at other coordinates such as Eddington and Finkelstein, and to see if there are better coordinates to describe this whole region, and that we can actually remove what appears to be a singularity, which in fact physically it is not, but this can be removed with a better choice of coordinates. And so other coordinates will be investigated in the videos to come. That is that.